Most people think waves travel across the ocean. They don't. Water isn't moving toward shore, not really. What you're watching is energy, pure energy, passing through the water like a message through a crowd. The water itself stays mostly still, bobbing up and down in place. This is the first thing that breaks our intuition about waves. We see them roll in and assume the ocean is rushing at us. It isn't. To understand why waves break, you have to start with what's really happening beneath the surface. A wave is a vibration. It's a disturbance that propagates through water, transferring energy from one particle to the next. Think of it like dominoes standing upright in a circle. Push one down and the motion ripples through the chain, but each domino returns to standing. The water does the same. In deep ocean, this works perfectly. A wave can travel thousands of miles without breaking. The water particles move in circles, down and forward, then up and back, then down again, completing their orbit as the energy passes through. It's elegant, stable. The wave maintains its shape because the water is deep enough that the motion doesn't interfere with the seafloor. But something changes as the ocean gets shallow. The seafloor begins to matter. When water depth drops below about half the wavelength, that's roughly the distance between wave peaks, the bottom starts to slow things down. The particles can no longer complete their circular motion. The bottom is in the way. Here's where the physics gets violent. The front of the wave, still in deeper water, keeps moving at its original speed. But the back of the wave, dragging against the shallow bottom, slows down. The wave is being compressed. The whole structure becomes unstable. The water at the top has nowhere to go but forward and down. This is the moment before the break. The wave face steepens. The peak rises higher than it should be able to. For a brief instant, the wave is fighting gravity and friction at the same time. It can't maintain this shape, something has to give. And then it breaks. The crest collapses forward and suddenly you have a wall of water moving, chaotic, full of trapped air. The organized circular motion of deepwater waves becomes a tumbling mass. This is the wave we recognize. This is what we photograph. But it's also the wave's death. But here's the catch, not all waves break. Some beaches don't have them. Some coasts never see a proper break, no matter how big the swell gets. Why? Because breaking depends on the slope of the seafloor, not just the depth. A gradual slope, like a typical sandy beach, gives the wave time to compress and steepen. The energy dissipates slowly. The wave has a chance to build into that dramatic breaking form. But a steep slope like a rocky cliff or a deep trench close to shore doesn't give the wave time to organize. The energy transfers too quickly. The wave never gets tall enough to break. Instead, the wave just rises and falls. It might surge up the rocks and crash, but it doesn't break in the classical sense. There's no hollow curl, no moment of suspension before collapse, just a wall of water meeting an obstacle. The angle of the seafloor also determines the shape of the break itself. A very gradual slope produces a rolling break, what surfers call a mushy wave. The energy spreads out over a long distance. Steep underwater canyons create sudden, violent breaks. The energy concentrates in a narrow zone. The wave explodes. Temperature matters too. Warm water moves faster than cold water. So a wave traveling from a cold region into warm water will actually speed up, and the shape changes. Cold currents can slow waves down. This is why some coasts, fed by upwelling cold water, have completely different wave characteristics than nearby regions. And then there's the wind. A strong offshore wind can hold back a wave's crest, keeping it from breaking. An onshore wind does the opposite. It accelerates the break, makes it more violent. The same swell can produce completely different waves depending on what the air is doing. So when you stand on a beach and watch the waves come in, you're witnessing a conversation between energy, water, land, and time. Each wave is solving an equation. Can I break? Should I break? What's stopping me? What's pushing me? The physics is answering in real time. The wave that breaks on your local beach is the product of a storm hundreds of miles away. The shape of the seafloor beneath you, the season, the time of day, and forces you can't see. It's a reminder that even the most ordinary moments, a day at the shore, are built on layers of invisible physics. Next time you see a wave break, pause for a second. That crest you're watching isn't water moving toward you. It's energy traveling, transforming, colliding with the world. And the reason it breaks the way it does is written in the seafloor, the temperature, the wind, and the invisible forces that shaped the ocean long before you arrived. Subscribe so you don't miss the next time we uncover the hidden physics hiding in plain sight. The science that shapes everything you see, from the smallest ripple to the fiercest storm. Subscribe so you don't miss the next time we uncover the hidden physics hiding in plain sight.